something, and electrons were perhaps being conveyed to this region. And, or it could be some sort of photoelectric effect that was occurring. This is just sitting on the bench. So we put this in a black box. We had made it. This is a black box, thick steel, containing lead lining to get rid of as much radiation as conceivably possible. And we found that there was almost no zone. So we've just done 3 or 4 experiments this way, 3 or 4 experiments sitting on the bench, and so far absolute consistency between the two. This is just fresh information, so we're not sure, but it's quite possible somehow that this aluminum is picking up radiant energy of some sort and transducing it into the growth of this kind of ordered water zone. So to summarize, what I've tried to demonstrate is that there are some interesting things going on next to hydrophilic surfaces, and that the water next to hydrophilic surfaces seems to be different. It's known to be different to at least a few molecular layers, but we found that this region not only extends very far, we're talking about 1 million or several million water molecular layers. The evidence shows that it seems to be liquid crystalline. It certainly excludes solutes. And the recent evidence using incident light and incident radiant energy of all sorts suggests that the buildup of these layers, which presumably requires energy of some sort, occurs as a result of radiant energy ultimately coming from the sun. Thank you. Yes, we did try that, and we found that the gold was excluded.
Okay, what isn't excluded?
Sometimes next to negatively charged surfaces, we tried negatively charged microspheres, and all the negatively charged microspheres were excluded. Then we tried positively charged microspheres. Some types of positively charged microspheres are excluded, and that rules out some kind of electrostatic effect. Other kinds of positively charged microspheres are not excluded. And we haven't pursued it to the point of figuring out why, but that's a very good question. It might be that those particular species of positively charged surfaces somehow distort or melt the water and then come right to the surface. We don't know.
It would be interesting to do an experiment where you had something that wasn't excluded at n equals 0 plus your polystyrene that is, and watch it very carefully.
We have that in mind. We haven't, we're trying to get the day to extend to 26 or 28 hours.
Jerry, I didn't understand your experiment with the DNL sugars and amino acid, because we in chemistry generally use DNL as a kind of a reference system if you don't have a chiral environment for having some contaminants which may affect your system. I mean, how you explain the difference between the D sugars versus the L, if I understood you correctly?
Yeah, this was a kind of side experiment. Wasn't the main point, but we started with the hypothesis that somehow this 270 nanometer absorption is a signature of this kind of water structure, because we see it very strongly next to Nafion or next to gels. So it seems to correlate very nicely with what seems to be water structure. So we raised the question, in other situations where you expect water structure, would you see the 270 nanometer? Now, I guess what was missing from my presentation, and which is perhaps what confused you, is we've been thinking the same questions you've been thinking about the origin of life. And one possibility for the nature's preference for L amino acids and D sugars is that somehow it fits in with the special ordering of the water, which may extend very far from the surface. So that was the hypothesis. And the results, at least in preliminary fashion, seem to fit, that we got the 270 nanometer absorption in the biological species, but we didn't get it in the non-biological ones. It's not conclusive, but it's just suggestive.
You don't have any evidence that the pockets which are formed of the water are chiral?
No, we don't. Absolutely not. I agree. Yeah.
Could you put up the slide where you had the UV and the IR spectra joined.
Yeah.
So it's curious that when you tune into 3 microns, where all the water will absorb the radiation, you get an enhancement. But when you tune in to near 270 nanometers, which is this new spectral feature associated with this proposed special phase of water, it drives it in the other direction.
No, it doesn't actually. It's 1.0 is the control value, and so all of these wavelengths increase the size. It's just that the relative increase of size, you can see the different wavelengths here and the different wavelengths here.
Well, so then it has a minimum effect, but
The
you
minimum
understand that?
It has a minimum, right here. But 270, let's see, where is 270? Yeah, the effect at 270, and the reason possibly for that, we haven't investigated this yet, is that it may depend on the water that's absorbed in the bulk rather than in the exclusion zone. So as I mentioned to you, that the exclusion zone water absorbs a lot of 270, but the ordinary water doesn't. And so perhaps that's the explanation for this. Not sure. But all the wavelengths have a positive effect. We noticed this first a couple of years ago. We took one of these specimens, it was sitting on the microscope, and overnight the size tended to decrease by 10, 20, 30%. And as soon as we turned on the microscope, immediately, before there was any heating, the thing started to expand again. So we began to think that there are some optical effects. And now these results were done fairly systematically, although, as I said, we can't compare, you haven't been able to compare the relative intensities here versus here, so we don't know how these two groups scale.
So going back to over here, going back to your very first experiments,
Yeah.
you show that there's an exclusion zone from the surface, but there's not an exclusion zone around the polystyrene particles themselves. And then later on you show a Nafion surface which has a point to it. And around the point, there's an insignificant exclusion zone as well. It suggests that the curvature of your surface is very important in these experiments.
Well, yeah, I mean, that's certainly a good point. In fact, we don't know if there's an exclusion zone around the microsphere because the microsphere is only 1 micrometer and the resolution of the optical microscope is, half a micrometer or something like that. So we can't tell. However, we've used larger spheres, and for example, we've used gel beads, the ones that you use for ion exchange beads, and there you can see the most beautiful exclusion zone surrounding the surface. Very, very clear, a few hundred micrometers.
So is there any evidence the size of the exclusion zone is related to the curvature of the material?
Well, again, that's a good question, and one must presume that the most relevant feature might be the size of the water molecule relative to the curvature of the surface, or to the roughness of the surface. In incidental experiments, we found that some roughened surfaces don't show this as well as smooth surfaces. So perhaps it's correct that you need a fairly smooth surface to give you a zone that's as vast as the ones that we've seen. But I want to just emphasize that curved surfaces do give you exclusion zones.
So I was wondering if you measured the kinetics of the microsphere separation from the exclusion from the surface.
Yeah, we've measured actually that I didn't mention it, but in one of the papers it's actually presented. And if you watch the time course of movement of the microspheres from the surface, the negatively charged microspheres is almost linear with time. It moves at constant velocity up until about 10% of the time it reaches the end. Then it quickly levels off and approaches 0. Then it stops. But you can then see very nice thermal motion.
Is it possible to affect this zone by addition of salt or addition of ethanol?
Yeah, we've done salt experiments, and salt tends to decrease the size of the zone. And it varies with different salts. And it varies in accordance with the Hofmeister series.
Can't resist that, sorry. I'm really interested in a sense why the hydrophobic surfaces don't seem to do anything, because the radiant energy explanations you're using doesn't sound like they would exclude them, okay, or explain why it doesn't happen at a hydrophobic surface.
Can't answer that because we've tried only a few such experiments and we gave up when we didn't see it. So the focus has been on the water structure rather than so much on what types of surface would nucleate it. But someone should do it.
From biological point of view, very important question, because biological system, it seems to me, all organized like layers of exclusion zone because we are making of cell. Do you try to study interaction between two exclusion zones? One from one side and another, maybe start moving, because the force between two exclusion zones can answer many important questions of processes happening in the biological system.
We haven't done that specifically, and it's a great idea. It's sitting in the back of my mind. We have tried a cylindrical geometry, and we use this very commonly. So you take a Nafion tube, right, and what you'd expect is an exclusion zone, an annular exclusion zone just inside, actually one just outside. And so the one inside approximates a little bit of what you're talking about. And we find that you get an exclusion zone, 200 or 300 micrometers as such. And even if you push the fluid through at high velocity, this exclusion zone is maintained. The size decreases as a function of flow velocity, but it's maintained and reaches a plateau even if you increase it enormously. So it doesn't quite answer your question, but of course we're interested in putting two together and also seeing what happens to the friction between the two. And so that's on the agenda.
Because here is a small comment, because if the force is relatively high, that probably could explain why we are from water but not fluid.
If the force is high,
Yeah, that is explain why we are not fluid, why we at least not
the force of what?
between two exclusion zones.
Oh, well, it was actually Albert St. Georgi who suggested first. You know, St. Georgi, the Nobel Prize winner who discovered vitamin C, he was talking enormously about water structure, long-range water structure. This is not something new, as many of you know. And he was saying that this structure is so important, is the basis of all of biology, and it's like an insulating boundary that keeps all molecules from coalescing into one big mass. That was one of the, it keeps them separated and keeps them together at the same time. So yeah, indeed, good question. Yeah?
Jerry, whoops. I just learned at lunch that if we replace all or half the water in a cell with D2O, that the cell catastrophically ruptures, and I'm wondering if you've tried replacing the water with D2O.
I didn't know that experiment, but it's interesting because we have tried it, and we've actually titrated H2O, D2O, and the size of the zone, the more D2O you put in, the smaller the zone becomes. So that wouldn't surprise me at all. Yeah.
Gerald, you mentioned that pro-oxidants and antioxidants somehow affected the exclusion zone. Did you reproduce these results?
Well, there is some effect, but I guess we haven't really studied it to the extent that I think where we could say something absolutely definitive. We started. Sorry. Yeah, Larry?
Have you degassed your water ever? Or do you use just ordinary water out of the tap? Distilled.
No, I know. Of course, we use distilled deionized water. If we use other kinds of water, then we find almost anything you add will decrease the size of this zone. The more pure the water is, the bigger the zone gets. So, but degassing, we have tried it, and I wish I could remember. The postdoc Jim Zhang did the experiment with degassed water, and if the results were phenomenally different, I guess I would remember it. I think there's not much difference, and I apologize that I don't remember exactly.
If you take the Nafion, say, and you've got this exclusion zone, the spheres are all kind of hanging off to the side. If you were to pull that away, perhaps slowly or perhaps quickly,
do the things, does the entire structure to the right-hand side, say, does that all move?
Yeah,
Or if
it
you
moves.
yank it out,
Yeah,
you
it
get
does
left
move.
with
It
some
exactly moves. It exactly moves.
And if you go quickly, can you take that sort of exclusion zone, will that stay to some extent without the Nafion propping it up? Is it semi-stable on its own?
Yes, it's semi-stable. The way we know it's semi-stable is that basically you're asking whether the structure is long-term. And
Yeah. The thing that was holding it, I mean, the original...
well, there are two things you're asking. First, if you yank it away, what happens? So you have a surface here, and you have the microspheres, and you try to yank one of the two away from the other. Well, you can see that this zone of water remains basically the same width, right? It's as though it's a semi-solid kind of structure. It follows exactly. We found the same thing at the air-water interface. We have a thick zone, and Adam Wexler, who's here, is the one who showed it first, and that at the top, here's the air-water interface, here's the air, and then it's full of microspheres. But there's a zone that has no microspheres that's approximately a few hundred micrometers, and it looks in many ways similar to the exclusion zone that I've been talking about. So Adam did the experiment. He picked up the top using a rod, and the water surface moved up by capillary action. And the interface between the microsphere region and the exclusion zone region followed exactly. So you pick up the air-water interface surface, it looks like a tent, and the boundary between the microspheres and the clear water followed exactly. And if you move one along, the other follows the same. So it looks as though this layer of water, whether next to the Nafion or the air-water interface, is somehow mechanically interconnected. And to answer that question. Sorry, the second part of your question was?
Is it possible to separate out a little piece of, let's
call
it ordered water,
sorry.
without that boundary next to it, and
Yeah,
have it hang around for a while?
So we find that you have an exclusion zone here. Here's a gel surface. Here's the exclusion zone. And if we set up the chamber geometry properly, this exclusion zone will actually come like this and extend out a meter, as far as a meter. It's a kind of like a stalactite, like a projection that comes out. In that region, you can have microspheres all around, but they never will enter that particular region. So it looks like this is a liquid crystal that's actually grown out along there. We can cut it, and we can cut it with an intense laser beam. And if you cut it, this distal region remains. So it stays for a long time. It stays for a long time. We didn't study it systematically, but it's obviously there, and it stays for a long term.
We are 5 minutes into the break, but if you wish to continue, we can continue. What do you say?
I don't want to dominate.
So if we recognize the historical controversy over water, and listening to your presentation, the one red flag is your proposal that water is crystallized. So what is the best experimental evidence that you have the crystallization of water in the exclusion zone? Does it diffract X-rays?
We tried X-ray, and we got nothing clear, and suggesting that that's wrong. However, in other words, we might expect to see some sort of diffraction pattern that was different from ordinary water. We didn't try it exhaustively. We tried it a few times, and the experiment failed. And so the fact that the experiment failed would suggest that it's not ordered. However, the kind of ordering that we'd expect in this liquid crystal couldn't be uniform because, for example, we measure the potential distribution across the zone, and it varies from one point to another. And the fact that it varies suggests that the net negative charge within this putative crystal is changing as a function of distance. If that's the case, then it's not a uniform crystal. So that would be one reason why you might not expect the diffraction that you'd expect from a real crystal. The second reason that you might not expect it is that the Nafion surface, or the gel surface, is not flat. And so as the Nafion absorbs water, it increases by approximately 30% in all dimensions. And so the surface, instead of being flat, is sort of corrugated. And so any structure that builds from the surface would not be a uniform structure. It would have reflect those corrugations. So those are two reasons why one might theorize that, although we had hoped to find some evidence of regularity. Those are two reasons to theorize why the kind of regularity that you might expect would be a kind of quasi-regularity. We're still pursuing this question to this day, and so I can't suggest that any one piece of evidence confirms that it's crystalline. But this is the suggestion from the evidence that I've presented. I'm not sure of what kind of alternative hypothesis one might put forth. Yeah? Well, I'd like to hear your experiment. I know you've done something similar and have gotten something that looks like a crystal. And so we should speak about that because, of course, also it takes us 1 or 2 minutes to do the X-ray diffraction experiment for each exposure. And during that time, a lot of things might be fluctuating and averaging out. So yeah, small region, very short time duration. And I think I should let these people go to coffee. Yeah.
The last comment.
Okay.
If you have a liquid crystal-like film of the order of tens of microns, that's almost like a liquid crystal display film. It's so easy to look at the birefringence from the optics.
Well, we've been looking at birefringence here with positive signs, but we haven't done the right controls yet to be sure that these experiments...
But you should be able to see whether it's a liquid crystal state or not.
We do. We see with cross-polarizers, we can see a region extends well into the water that looks like it's liquid crystalline, indeed. And so as Artmann's group in Germany found the same thing. It's just that we can't be certain yet because the controls aren't yet done. So that's why I'm not sure.